So what's up, everyone? I've been sitting on this case study for a little while now. I wasn't able to do this case study for various reasons that I can't get into, but I can now. So we're going to go over this case study that I've had for say about a year now. It's a 2007 4Runner, and I say it's a 4Runner from hell because this thing beat me up pretty bad. I made a couple mistakes. They weren't big mistakes, but I definitely would do a couple things differently if I had this car again. And it had multiple failures that just didn't seem to end. So this vehicle got towed in is a no crank. What I will say is that I checked my starter relay. Now you have to be very cautious when checking this starter relay. You cannot remove this starter relay to check the relay. So keep that in mind. But anytime I had a tow-in come in, I would just take a test light out with me and I would just do a couple basic checks. And what I realized was I was not getting command on this wire. Now understand that when we put 12 volts on this wire, we create a magnetic field because we are grounded, right? We have current flowing through windings. We create a magnetic field which closes this switch. Now when that switch closes, we should have power coming from the battery through the AM2 fuse into our starter. But we had no 12 volts being sent to this wire when testing with a test light. Now again, you cannot remove this relay completely, so you have to just pop it up just a little bit just to be able to touch the leg. Now why am I emphasizing the fact that you cannot remove this relay to test the contacts on it? Alright, first you need to know how this circuit actually operates. When you turn your ignition switch on, right, to the start position, we're going to send power from our battery through the AM2 fuse into our ignition switch. When we're in the start position, we send power to the ECM on the STSW circuit. When the ECM sees power on that STSW circuit, it now needs to determine if the vehicle is in park or neutral. If it's not in park or neutral, it will not send power to that starter relay. But how does it know if it is in park or neutral? That's where removing the relay can get a couple people bound up. Alright, so on your park neutral input switch, right, we have our neutral start switch circuit that outputs 12 volts on this circuit. It goes through the park and neutral switch. If the park neutral switch is in park or neutral, we send power, we send 12 volts through a couple junction connectors through our starter relay into ground. Alright, now let's think about this for a second. If we send 12 volts from our engine control module out to the relay just to check for park or neutral, wouldn't the relay always be on? Well, that's not actually the case. What isn't shown in the wiring diagram is a lot of these signal circuits have resistors inside of the ECM. So inside of the ECM, you have 12 volts going through a very large resistor. Right? We're talking about probably somewhere in the realm of 100,000 ohms. This resistor is. Now, the relay, relative to the resistor inside of the ECM, the relay has low resistance. Again, in relation to the resistor inside of the ECM. So all of your voltage drop is going to be taking place on this resistor. So when this circuit is closed, you actually have 0 volts, right? Because we have a ground path through our relay windings. We are using the relay as a ground path. So I have this little demo set up. What I want to show is I have a very high resistance light bulb in relation to a relatively low resistance light bulb. I have 12 volts going into this light bulb, and this red lead goes to my multimeter, so you can see that I have 12.6 volts on the ground side of this light bulb, because I do not have my ground path hooked up, I am going to ground this light bulb with this light bulb to show that this light bulb will light up because it is dropping all of the voltage. You'll notice I have near 0 volts when I ground this on my voltmeter reading. And you will also notice that this light bulb does not light up. So this is showing that the relay in the car will not operate, even with 12 volts essentially being supplied to it. It's because it's 12 volts through a high resistor. So, as I touch this to ground, notice this light bulb lights up, my voltage drops to near 0, and this bulb does not light up. So this is how that neutral start switch actually operates. If you were to remove this light bulb or this relay from the circuit, right? So we remove this relay from the circuit. I have 12 volts on this circuit. This is now telling the ECM that I do not have this vehicle in park or neutral. And without this vehicle being in park and neutral, guess what? The vehicle will not send command to that relay to turn on. So now, once we have all of that worked out, how does this work? How does this send power to the relay to actually energize it? So we have this additional circuit. I think it's called the STA circuit. Don't quote me on that. But we have 12 volts, a 12 volt driver inside of this ECM. When it both verifies that STSW is turned on and the NSW switch is at 0 volts or near 0 volts, it then will power on this 12 volt driver. And you'll have 12 volts on a second circuit that does not have a resistor going from ST1 through a couple junction connectors, then through our relay, right? But because there's not a resistor inside of that STA circuit, we now can give full power to that relay. Vehicle should crank, so on and so forth. Now, what I found was that in one of these connectors, I had large amounts of corrosion. Now, this here is in a kick panel. One thing about Toyotas is if you do have an electrical issue, check those connectors in the kick panel. They are notorious for having corrosion buildup in them. So this here is one side of the harness, and this here is the other side of the harness. Now, both of these harnesses, it's two separate harnesses, I believe was like $5,000-$6,000 just in parts, didn't include labor, right? So these are very expensive. The customer just asked me to completely remove both harnesses, so I had to splice all of these bad wires together and bypass this connector, which I did. So this is why I should have taken a Scantle out with me when the vehicle was originally towed in. I had no communication with any module. Vehicle still would not start. No communication with the yaw rate sensor, steering angle sensor. Nothing on the CAN network would communicate. So I looked at my CAN messages. Right, so this here is not a good CAN message. I still had my 2.5 to say 3.5-ish, maybe a hair over 3.5, and then 2.5 down to near 1 volt. But the problem is these packets were just repeating, and these are not good packets. This means nothing to anything. And it was just a repetitive message that would not change. It was the constant same message being put out onto the network. Now, if you would unplug the ECM, this is what your CAN network would look like. You go from 2.5 up to about 3.5, and then 2.5 down to 1.5 on our CAN high and CAN low. What did that tell me? That told me that I had a failure with my ECM. When it was plugged in, it looked terrible, and the network wouldn't shut up. But when I unplugged it, the network kind of cleaned itself up. So I replaced the ECM and did the handshake. Okay? So I installed the used ECM. Vehicle now starts. Vehicle still runs. But the vehicle will not go over 44 miles per hour during a test drive. All right? So now fixed the wiring to the starter relay. And I have a feeling that one of those wires maybe jumped 12 volts to somewhere on that ECM that it shouldn't have had, which took out that ECM. But here's a question. Let's just say, hypothetically, I went out with a scan tool and I seen the no communication, and then I chased the communication fault first. Well, I still would have had the electrical issue that I had to fix. So even though I say I made a mistake by going after the electrical issue before the ECM issue, it all ended up working out for the best. The problem is, it would have been nice to be able to tell the customer that you had a no communication fault and a wiring fault at the same time. Right? So this vehicle will not go over 44 miles per hour no matter how hard you hit that gas pedal down. At this moment, I was not there. I had my apprentice looking at this. My wife was having surgery that day. Like I said, this was a while ago. She's fine. My wife was having surgery that day, and while I was in the waiting room, I was helping my apprentice program the ECM, and then during the test drive, I was helping him try to diagnose this. What he found, and what some coworkers helped him with, because like I said, I wasn't there, the transmission speed sensor SPS2 was reading 112 miles per hour. Now that's as fast as a 4Runner will allow you to go. All right, just to put this into perspective, when I was going about 9 miles per hour, SPS2, can you see it? SPS2 was reading 25 miles per hour, right? So I was going 9-10 miles per hour. SPS2 was saying that I was going 25 miles per hour. Now, what I'm going to say is this vehicle has either four-wheel drive high, or four-wheel drive low. It does not have two-wheel drive. But if you see this little button here, that is the locker, all right? So this has an open transfer case and an open rear differential. So even when it's in 4 low, it's just a gear ratio change. It is not, it does not feel like it's locked up, right? So if you put a vehicle in 4 low, let's just say you have a truck, and you put it in 4 low with transfer case or differential locked, going around bends, it's gonna lock and bind up. Putting this particular vehicle in 4 low and not locking differentials, it's gonna feel just like a dog. It's just a gear ratio change. And that is what my coworker was talking about. Again, I was not at work this day. He thought that it was in 4 low, but there's no lights on the dash saying that it's in 4 low. And it doesn't feel like it's in 4 low. Or it at least doesn't bind when going around bends. So how do we prove that this thing is actually in 4 low when nothing is actually telling us that it is? And keep in mind, on this particular model 4Runner, there's no data list for the 4-wheel drive system. There's absolutely no data list at all. So it's not as easy as hooking up a scan tool and looking at your data PIDs. So what my coworker found out was that in full-time 4-wheel drive, so 4 high, we had a 1-to-1 gear ratio. But when we were in 4 low, we had a 2.566 gear ratio. Now think about that. Our SPS2 was reading about 2.5 times higher than it should have been. Okay? If we go back, we were going 10 miles per hour, but we were reading about 25 miles per hour, which makes sense if the vehicle is in 4 low, right? The math adds up. So now we had to prove it. There's one circuit in here that tells the ECM if you are in 4 high or 4 low. All right, so when you have your 4-wheel drive control ECU, we have a signal to the engine control module. All right, so the engine control module is going to output 12 volts on this circuit, again through that resistor. And when the 4-wheel drive control ECU determines that the vehicle is in 4 low, it's going to ground that circuit and put it, it's going to ground that circuit, and your voltage is going to drop to 0 volts or near 0 volts. So now we have to test this and make sure it's all right. Okay. So I tested the voltage on the L4 circuit that should be grounded by this 4-wheel drive ECU. And I had 12 volts on it. So what we were able to determine is that this 4-wheel drive ECU was not grounding this circuit. So what would happen if the vehicle is actually in 4-wheel drive or 4 low, but this circuit was not grounded? The ECM wouldn't know, right? And the gear ratio change is causing SPS2 to read higher than it should because of the gear ratio change. But the ECM can't do that calculation properly because it doesn't know that the 4-wheel drive circuit is, or the 4-wheel drive system is engaged. The 4 low system, I'm sorry. The 4 low system is engaged because this circuit isn't grounded. So if we add our own ground through a light bulb, just like I did on the bench, we drop that voltage down to 0 volts. And then we're going to drive this vehicle again, right? Now, the ECM is fully aware that 4 low is engaged, and mathematically, everything lines up. I'm going about 8, 9 miles per hour. SPS2 on my data PIDs for the ECM is reading 8 miles per hour. So, all of this to say that my transfer case was in 4 low, but my ECM thought that the vehicle was in 4 high. And the algorithm inside of that ECM just wasn't allowing this vehicle to go over 44 miles per hour, because at 44 miles per hour, it thought that the car was actually going about 112 miles per hour. All right. Now, how do we actually fix this car? Keep in mind that this guy has now spent a lot of money on this vehicle. It's a vehicle that he doesn't intend to keep much longer. So we needed to force this thing back into 4 high. So what we did is we added a power probe. We just shoved this motor back into 4 high while somebody was tapping on that actuator. Told him, do not touch your 4 low button because it will get stuck again. But we were able to force this transfer case back into 4 high. We drove the vehicle, and we were able to go over 44 miles per hour at this point. So just wanted to share this case study with you all. I've been sitting on it for a while. I hope you enjoyed it. If you have any questions or comments, leave them down below, and catch you all next time.